Dear students, I welcome you all to this one semester undergraduate level course on thermal physics. Let's go through the syllabus and main topics briefly that we will study during this course. At the end, I will also recommend you few text and reference books. We will start with the thermodynamic description of a system, in which we will study various thermodynamic processes like isobaric, adiabatic, isothermal, isochoric. We will learn the thermodynamic coordinates or variables and their types like intensive, extensive. We will study all the four laws of thermodynamics, starting with zeroth law, and we will see how the concept of temperature evolves from zeroth law. Then we will see how the concept of internal energy is given by first law, and we will learn how we can convert heat into work. That is the main core theme of thermodynamics. In the applications of first law, we will derive a relation between molar specific heat at constant pressure and molar specific heat at constant volume. We will also derive expressions for work done during isochoric process, which is of course zero, work done during isobaric, during adiabatic, and during isothermal processes. We will also learn what do we mean by compressibility and expansion coefficient. And we will also study how we can differentiate between reversible and irreversible processes. Coming to second law, which gives us the concept of entropy, we will learn Carnot cycle and Carnot storm. We will see what is the entropy change in various processes, especially reversible and irreversible. We will plot a graph between entropy and temperature, which are called entropy temperature diagrams. We will learn how absolute zero, that is 0 Kelvin, cannot be attained. The concept comes from the third law of thermodynamics. And in analogy to mechanics, four thermodynamic potentials are defined: internal energy, Helmholtz free energy, Gibbs free energy, and enthalpy. We will also derive Maxwell's thermodynamic relations, and we will see that we can apply those relations to explain Joule-Thomson effect. Also, we can derive Clausius-Skilla-Perron equation. We can derive an expression for Cp minus Cv, which is also called the heat capacity relation. We will also derive the expression for ratio of specific heats. We will also derive the three TDS equations, and we will learn what are their physical significances. We will also learn that how the gases we encounter in real practice in day-to-day life are real, and they are not ideal. They don't behave as ideal gases. They don't obey the gas laws and the ideal gas equation in all the circumstances. To account for this deviation, we will learn about van der Waals equation of state and other equations of state, and we will also compare this theory with the experimental results. We will also know what are the critical constants, critical temperature, critical pressure, critical volume, and in the liquefaction of gases, we will learn what do we mean by Boile's temperature, inversion temperature, and why these two temperatures are significant when we consider liquefaction of gases. We will also learn three methods of cooling: regenerative, cascade, and adiabatic demagnetization. In the kinetic theory of gases, we will start with the basic assumptions of kinetic theory, and subsequently we will derive the kinetic theory equation, which is just an expression for pressure of a gas. We will also study what is the classical theory of heat capacities, and how does it not uh, uh, is not compatible with the experimental results, especially at low temperatures. We will also derive the Maxwell-Boltzmann distribution law of velocities. We will study also the Zatman co-experiment, which verifies this distribution law. We will study how we can apply law of equipartition of energy to determine molar specific heat at constant volume, molar specific heat at constant pressure, and their ratio. And finally, we will complete our course with mean free path, the three transport phenomena, thermal conduction, viscosity, and diffusion in gases, Brownian motion, and random walk problem. Now let's come to the books. For students, I will highly recommend that you start with the Brij Subhramanyam and Hemne book. Then next, you can go to the Garg Bansal Ghosh book. For students, I will recommend that the first two books will suffice you. For teachers, I will go beyond these two books. You may study the Zamansky and Dittman book, Sears and Salinger book, and also Daniel Schroeder.